Okay, let's unpack this. We are tackling, well, one of the biggest questions, isn't it? Are we alone? It's a question that's evolved over millennia, changed shape completely. Philosophy, religion, science. It's touched everything.
It really has. It's quite an epic journey when you trace it back. And that's what we're going to dive into today, really getting into the history of this idea.
Okay.
Our main guide here is Joseph Shklovsky's work, Universe, Life, Reason. A pretty revolutionary analysis for its time.
Right. So our mission, if you like, is to give you the essential background, the shortcut, really, to understand how this whole search for life beyond Earth actually transformed over time. We're going from, ancient cults and ideas that got people burned at the stake,
Literally.
right up to the hard science, astrophysics, genetics, the stuff driving the search today. And I think the big surprise for many people is that this isn't just a modern space age thing. The roots go deep. Way back when astronomy itself was, well, barely getting started.
Yeah, understanding that long view is crucial. It's the context for everything else. It explains why we pour resources into things like SETI, trying to listen for signals, or why we spend so much time and effort looking for microbes on Mars. We're wrestling with a question that's fascinated thinkers for literally thousands of years. Yeah. But the difference now is we finally have the scientific tools to maybe, just maybe, find some real answers.
Okay, so let's start at the beginning. The really deep roots. It didn't kick off with science as we know it, did it? It was more metaphysical.
Spiritual.
Exactly. The very first glimmerings of the idea, they probably came from primitive cults. These early cultures often animated the world around them. The sun, the moon, the stars. They weren't just objects, they were places, or even beings. They had agency.
And that connection to religion stuck around. Shklovsky points to Buddhism, right?
Yeah.
Yes, he does. In Buddhist thought, the idea of multiple inhabited worlds gets tied up with the concept of soul transmigration. Reincarnation, essentially. The sun, the moon, the stars. They weren't just points of light. They were actual destinations, places where souls might reside between lives or on their journey towards nirvana.
So the universe was already populated in a spiritual sense long before anyone proved planets existed.
Functionally populated, yeah. It's a very different worldview. But then as we move towards ancient Greece and observational astronomy starts to, take its first real steps, the ideas begin to shift. They become more physical, more concrete.
And the Greeks, well, they really ran with it, didn't they? Even with just their naked eyes.
It's actually astounding what they came up with. Considering their limitations, it's brilliant. And what's fascinating is that across the board, materialists, idealists, different schools of thought, most Greek philosophers landed on the same conclusion. Earth is not unique. It cannot be the only place with life.
They just rejected cosmic loneliness right out of the gate.
Pretty much. It seemed illogical to them. And you can see a progression. You have Thales, for instance. He taught that the stars weren't fundamentally different from Earth. Made of the same basic stuff.
Which implies, if the ingredients are the same,
then the potential for similar outcomes, like life, must be there. It's a basic argument from commonality. Then you get Anaximander talking about worlds coming into being and being destroyed, a kind of cosmic recycling.
But the really mind-blowing one, the one that feels almost modern, is Anaxagoras.
Anaxagoras, yes. He was pushing boundaries, suggesting the sun was the center, not Earth, claiming the moon was inhabited. But his truly radical idea, the one that echoed down the centuries, was about life seeds. Sperma, he called them.
Invisible seeds, everywhere.
Invisible, yeah. Scattered throughout the cosmos. And these seeds were the fundamental origin of all living things. Basically, life wasn't something that had to start from scratch everywhere. It was already latent, waiting for the right conditions.
That sounds incredibly close to panspermia.
It's the philosophical ancestor, absolutely. Yeah. This idea of is veknos dzizni, the eternity of life. Life is omnipresent, eternal. And interestingly, Shklovsky notes that early Christianity actually flirted with adopting this idea, trying to weave it into their own cosmology about eternal life.
Wow. Okay, so that idea has serious staying power. Moving on a bit, the Epicureans really leaned into the probability argument, didn't they? Mithridates and his analogy.
Oh yeah, the wheat field analogy. It's probably the most quoted soundbite from this whole ancient period. The Epicureans were staunch believers in countless worlds, very much like our own Earth. And Mithridates put it so simply, you didn't need to be a philosopher to get it. He said basically, to think Earth is the only inhabited world in boundless space is as absurd as saying only one stalk of wheat could grow in a giant field.
It's just common sense applied to the cosmos. Uniqueness seems silly when the scale is so vast.
Precisely. And for them, worlds wasn't strictly planets like we think of them. It was a broader term. Lots of celestial bodies, all potentially hosting life, scattered everywhere. A densely packed universe.
And this influenced the Romans too. Lucretius Keros.
Deeply. Lucretius, the Roman materialist poet, he was a huge champion of this idea. Very vocal, very passionate about it. He wrote it into his epic poem, On the Nature of Things. Made it accessible.
What did he actually say? Is there a specific quote?
Yeah, there is. He wrote, "This whole visible world is not the only one in nature, and we must believe that in other regions of space, there are other lands with other people and other animals." Just laying it out there. Other lands, other people, other animals. Pluralism, plain and simple.
But there was a catch, wasn't there? Something about his understanding of stars.
Ah, yes. Here's where the limits of their science really show. Lucretius was completely wrong about what stars were. He thought they were just like glowing vapors rising from the earth, kind of like distant campfires.
Seriously, glowing earth steam.
Basically, yeah. So because he had that wrong idea, he couldn't logically put his inhabited worlds around those stars. He had to imagine them existing somewhere else entirely, outside the visible starry sky we see.
So he argues for infinite worlds, but his physics forces him to place them beyond infinity almost.
Kinda, yeah. It shows the strength of the belief in pluralism was there. Powerfully so. But the scientific framework to actually place that life correctly within solar systems orbiting stars, that was missing. The physics needed about, 1,500 years to catch up with the philosophy.
Which brings us neatly to that huge gap, that 1,500-year silence. What happened? Why did this vibrant discussion just stop?
Well, one word. Ptolemy. Or rather, the system named after him. The geocentric model. It wasn't just an astronomical model. It became deeply embedded in the structure and theology of the dominant power in Europe. The Christian church.
Earth at the center, humanity at the center, God's special project.
Exactly. And if Earth is the unique focal point of all creation, the stage for the divine drama of sin and redemption, then other inhabited worlds.
Yeah.
That's a huge problem. It dilutes humanity's special status. It raises awkward questions about God's attention, about salvation on other planets. It was theologically dangerous.
So the idea was actively suppressed for over 1,000 years.
Effectively, yes. Discussing it, promoting it, became heresy. It challenged the entire cosmic order that underpinned religious and political authority. But then, Copernicus, mid-16th century, everything starts to shift.
The Copernican revolution, putting the sun back in the center.
And in doing so, Copernicus didn't just rearrange the cosmic furniture, he fundamentally demoted Earth. Suddenly, we weren't the center of everything. We were just another planet, one of several orbiting the sun.
And that demotion was the key, wasn't it? The first real scientific foothold for pluralism.
Precisely. If Earth isn't unique in its position, why assume it's unique in its inhabitants? The logic starts to flip. And very soon after Copernicus, we get Galileo and the telescope.
Seeing is believing.
Right.
What did Galileo see?
He saw that planets weren't just points of light, they were worlds, physical places. He looked at the moon and saw mountains, valleys, craters, features just like Earth's, not some perfect celestial sphere.
And people immediately thought,
If the moon looks like Earth, why not cities? Why not moon people? It wasn't abstract philosophy anymore. You could see the potential right there through the eyepiece.
but turning that potential into a public declaration, that was still dangerous.
Which brings us to Giordano Bruno.
Ah, Bruno. The martyr for the cause, you could say. He wasn't just looking, he was thinking, connecting the dots. He understood the radical implications of Copernicus and Galileo, maybe better than anyone at the time, and he wasn't afraid to say it out loud.
What was his core message?
He took Copernicus to the next logical step, beyond just our solar system. He said, famously, and this is what got him into so much trouble, there are countless suns, countless Earths that revolve around their suns, just as our 7 planets revolve around our sun. Living creatures inhabit these worlds.
Countless suns, countless Earths. He saw an infinite populated universe.
He did. A universe teeming with life. And for that vision, for that clarity.
The church's response was final, brutal. He was tried by the Inquisition, declared an unrepentant heretic, and on February 17, 1600, in Rome, Giordano Bruno was burned alive at the stake.
Burned alive. For suggesting other worlds might have life, it's hard to even fathom that today.
It's a chilling reminder of the cost of challenging established dogma. It was a violent attempt to extinguish a revolutionary idea. But ultimately, you can't burn an idea forever. Shklovsky points out that the churches, both Catholic and Protestant, eventually had to adapt. They couldn't keep fighting the tide of scientific evidence.
Forced adaptation, then.
Pretty much. Over time, they slowly found ways to reconcile the possibility of life elsewhere with their core beliefs. They had to concede that maybe God's creation was bigger and more diverse than they'd initially imagined.
Okay, so Bruno pays the ultimate price, but the idea survives. And by the 17th, 18th centuries, it's basically mainstream among thinkers.
It really takes off. It becomes almost the default position for educated people, for the leading lights of the Enlightenment. You've got writers like Cyrano de Bergerac. Yes, that's Cyrano writing about trips to the moon. Fontenelle's Conversations on the Plurality of Worlds was a bestseller. Scientists and philosophers, too. Huygens, Voltaire, Kant, Laplace. The list goes on. Even Russia's great scientist Lomonosov was on board, just widely accepted.
But acceptance doesn't always mean accuracy, right? This is where we get some really wild ideas, even from brilliant minds.
Oh, absolutely. The enthusiasm often outpaced the actual data, and the prime example, the weirdest one, has to be the inhabited sun.
The sun, as in the giant ball of burning gas. People thought things lived there.
Not just people, but scientific giants.
Mm.
William Herschel, the guy who discovered Uranus, a brilliant observational astronomer, he was convinced the sun was inhabited.
How did he even rationalize that? The heat, the light.
He came up with this elaborate model. He thought the blazing part we see was just an outer layer, like luminous clouds. Underneath those clouds, he imagined, was a solid, dark, cool surface, and sunspots. He thought they were temporary holes, openings in the bright clouds, allowing the sun dwellers to peek out and see the stars.
Wow, okay, that's creative. And he wasn't alone.
Nope. Isaac Newton apparently held the same belief. Two of the greatest scientific minds of the age, both convinced the sun had residents living on a cool interior shielded by fiery clouds.
It just shows how powerful the assumption of life was, doesn't it? They expected life everywhere, so they found ways to make it fit, even in the most unlikely places. They defaulted to similarity.
Exactly. If life exists here under these conditions, they reasoned, it must exist elsewhere under similar conditions, even if you have to invent a bizarre scenario like a cool sun interior to make it work. But, even in an era of almost universal belief, there were a few voices urging caution. People saying, hold on, maybe not everywhere is suitable.
The early skeptics, who were they?
One significant factor Shklovsky mentions is William Whewell, writing around 1853. He was quite brave for his time, pushing back against the overwhelming consensus. He looked at the planets and started applying some basic physics and chemistry.
What did he argue?
He pointed to the giant outer planets Jupiter, Saturn, and said they're probably just huge balls of water, gases, and vapors. Not solid surfaces suitable for life as we know it. Remarkably close, really. And crucially, he talked about proximity to the sun. Too close, like Mercury perhaps, and it's too hot for liquid water. That's an early formulation of the habitable zone concept. He also correctly stated the moon couldn't support life.
So introducing actual physical constraints, not just philosophical desire, that's a big step.
A huge step towards a more scientific approach. But even so, the urge to find life somewhere nearby was strong, which leads to some other rather strange ideas even later in the 19th century. Well, there was the astronomer V. Pickering. As late as the 1890s, he was studying the moon, observing changes on its surface, probably just shadows or atmospheric distortion, you know. But Pickering interpreted these changes as mass migrations of lunar insects. Insects on the moon migrating. Swarms of them, apparently. It sounds completely bonkers now, but it shows the sheer will to believe. People wanted to find neighbors. And Shklovsky notes this insect idea even got briefly recycled later for Mars.
Okay, lunar insects aside, who was really driving the popular excitement back then? You mentioned Fontenelle earlier, but later on...
That would have to be Camille Flammarion, French astronomer and writer. His book, The Plurality of Inhabited Worlds, was an absolute sensation. Went through something like 30 editions in France alone in just 20 years. He really captured the public imagination.
But Shklovsky has some criticisms of Flammarion, doesn't he? Says he was more emotion than science.
Yeah, that's the critique. Flammarion was incredibly passionate, very categorical in his claims about life everywhere. But Shklovsky argues that his certainty was way out of proportion to the actual scientific knowledge available at the time. Astrophysics was still just getting started. Flammarion was coming from an idealistic standpoint. He seemed to believe that life was the ultimate goal or purpose of planets forming, almost a cosmic destiny, rather than a potential outcome of chemistry and physics.
So more philosophical conviction than hard evidence, even then.
A lot of it, yeah.
Yeah.
He was tapping into that deep-seated human desire to not be alone, but maybe getting ahead of the data.
Okay, moving into the late 19th and early 20th century, the science starts getting more specific. And that old idea, panspermia, makes a comeback. But with a proposed mechanism this time.
Right. The core idea is the same. Life isn't created spontaneously, it's eternal, and it travels between worlds. But now Svante Arrhenius, the Swedish chemist, proposed a plausible physical way for it to happen.
How did he think life could hop between planets or even stars?
His idea involved tiny living particles, hardy spores or bacteria hitching a ride on small dust grains. These microscopic grains have a huge surface area compared to their mass. Arrhenius calculated that the pressure from starlight itself could be enough to push these dust grains, carrying their living cargo, across the vacuum of space.
Light pressure, like wind pushing a sail, but with photons.
Exactly. He argued these spores could survive the cold and radiation of space for long enough periods. If they eventually landed on a welcoming planet, they'd wake up, germinate, and boom, life begins.
It sounds quite elegant, actually, using known physics. So why don't scientists widely accept it today? What's the problem?
There are a couple of major issues that emerged with more knowledge. First, the mechanism itself, while plausible for maybe moving between planets in the same system, gets really problematic for interstellar travel. The sheer distances, the radiation exposure over potentially millions of years, the harsh conditions of the interstellar medium. It seems incredibly unlikely that a spore could survive that journey intact and viable, especially on a tiny dust grain being pushed around.
So the trip itself is probably lethal over those distances. What's the other reason? You mentioned a cosmological flaw.
This is the big one. This undermines the fundamental assumption of panspermia, which is that life is eternal. Modern cosmology, based on hard evidence like the cosmic microwave background radiation, the echo of the Big Bang, tells us something crucial about the early universe.
What's that?
That about 13, 14 billion years ago, the universe was incredibly hot, incredibly dense, and made of almost nothing but hydrogen and helium, a simple primordial plasma.
Okay, not exactly ideal conditions for life as we know it.
Not at all. Life, certainly life based on complex chemistry like ours, needs heavier elements. Carbon, oxygen, nitrogen, iron, silicon, all that stuff. And those elements didn't exist right after the Big Bang. They had to be forged inside stars, right? Yeah. And then scattered when stars die. Exactly. Through generations of stars, living and dying, the universe gradually gets enriched with these heavy elements. It's a process that takes billions of years. So life couldn't possibly be eternal. It couldn't exist before the necessary ingredients existed. It had to wait until the universe had evolved enough, cooked up enough heavy elements, and formed stable planets.
So cosmology basically puts a time limit on when life could even start. Game over for eternal life seeds floating around forever.
Pretty much. Life is a product of cosmic evolution, not a primordial constant. That's a fundamental shift in understanding. Now, while this debate was happening, you had thinkers looking at the implications differently, like Konstantin Tsiolkovsky, the Russian rocket pioneer.
The father of astronautics. What was his take?
Well, he shared that basic conviction pluralism, echoing the ancients with analogies. He asked things like, can you have one inhabited island and all others empty? It seemed improbable to him. But his really key insight looking forward was about the diversity of life and civilization out there. Unlike earlier thinkers who kind of imagined aliens as just variations of humans on Earth, Tsiolkovsky grasped the implications of cosmic timescales. He realized that different worlds would be at vastly different stages of development. Some might have primitive life, some might have civilizations like ours, but others could be millions or even billions of years ahead of us. He said you expect to see all phases of development scattered across the planets.
That's a profound thought. We shouldn't expect mirrors of ourselves. We should expect anything, from microbes to godlike beings, potentially.
Precisely. It introduces the idea of immense civilizational asymmetry, a crucial concept for SETI later on. But before SETI could really take off, there was one last major scientific hurdle in the early 20th century that made life seem incredibly rare again: the genes hypothesis.
What was that about? Another theory of how planets form?
Yes, and it was the dominant theory for a while. Sir James Jeans proposed that our solar system formed from a freak accident, a near collision between our sun and another passing star. The gravitational pull of the passing star supposedly ripped a filament of gas out of the sun, and that filament then condensed into the planets.
A near collision between stars. That sounds exceptionally unlikely.
Exactly. Stars are incredibly far apart. The odds of such a close encounter are astronomically small. So if planet formation required such a rare catastrophe, the conclusion was stark. Planetary systems must be vanishingly rare.
Meaning life would also be incredibly rare. Maybe just us.
That was the prevailing scientific view for quite a while in the early 1900s. In a galaxy teeming with billions of stars, maybe ours was the only one lucky enough to have planets and therefore potentially life. It was a period of cosmic pessimism, scientifically driven.
But that hypothesis didn't last. It collapsed.
It collapsed in the 1930s. Calculations showed it just didn't work. It couldn't explain the angular momentum we see in our solar system, how the planets move. And as the genes hypothesis fell and astrophysics advanced rapidly, new theories emerged. Theories based on planet formation being a much more common, natural process like dust and gas accumulating in a disk around a young star.
Making solar systems the norm, not the exception.
That became the new thinking, yeah. A probabilistic assumption that planets should be everywhere. And of course, starting in the 1990s, we began finding them, exoplanets. First a few, then dozens, hundreds.
And now thousands, right?
Thousands confirmed. The editor's note in Shklovsky's later editions mentions nearly 200 by 2006. Seemed amazing then. Now, we know planets are utterly commonplace. That discovery, that empirical proof, completely demolished the last major cosmological reason to think we might be alone. The universe is packed with potential real estate.
So question shifts, not are there planets, but which planets have life? And that brings us to the modern era, where it's less philosophy and more. It's lab coats and telescopes.
And computers and gene sequencers, yeah. It becomes a truly interdisciplinary problem.
Huh.
Astrophysics is still vital, but its role changes slightly. Now, stellar cosmogony, understanding stars, is about determining habitability over time. Meaning, it's not enough for a planet to be in the Goldilocks zone right now. Life, especially complex life, needs stability, billions of years of it. So we need to know, how old is the star? How long will it remain stable, providing consistent energy? Will it flare up violently? Will it swell into a red giant too soon?
So astrophysics helps us identify stars that are good long-term hosts for life. It even tells us about our own sun's future and Earth's ultimate deadline.
Right. It sets the boundary conditions and tells us where and for how long the stage might be set. Yeah. But then the really tricky part, the core question, moves into the realm of chemistry and biology.
Here's where it gets really interesting, you might say. How does life actually start?
Exactly. It's fundamentally a chemical problem. Under what specific conditions can complex organic molecules assemble themselves into the first simple, self-replicating structures we'd recognize as living? And this is where the breakthroughs in molecular biology and genetics in the mid to late 20th century were absolutely transformative.
You mentioned DNA and RNA. Shklovsky talks about understanding their cybernetic meaning. What does that mean in plain English?
It means seeing DNA and RNA not just as complex chemicals, but as an information storage and processing system. Cybernetics is about control and communication. Life, at its core, is an information system. It stores the blueprint, DNA, copies it, replication translates it into action, proteins via RNA, and crucially, it evolves the information, changes, and adapts over time.
Got it. So the origin of life isn't just about getting the right chemical soup. It's about how that chemical soup starts storing and copying information.
Precisely. It reframes the origin of life as essentially a genetic problem.
Yeah.
How does that information system arise from non-living chemistry? And the progress in molecular biology has been so immense that scientists became optimistic, and many still are, that we're close to figuring out the precise pathways. Understanding that would tell us how likely or unlikely life's origin might be elsewhere.
Okay, so we have the astrophysics setting the stage, the biochemistry writing the first act, and then comes October 4th, 1957, Sputnik. Everything changes again.
A complete phase shift, not just scientifically, but psychologically, for humanity. Shklovsky uses this great phrase. He says, people suddenly understood weightily, crudely, visibly, that they lived on a tiny planet in a vast cosmos.
Before that, even if people knew it intellectually, they acted differently.
Yeah, he calls it practical geocentrism. We might have known Earth was a planet since Copernicus, but we acted, organized our societies, planned our futures as if Earth was the only stage that mattered. Sputnik shattered that bubble. Suddenly, space was real, reachable. Other worlds weren't just abstract ideas, they were potential destinations.
And the question of life there became practical too, testable.
Within the solar system, yes. It shifted from pure theory to experimental science. We started sending probes, designing life detection experiments to put on the surfaces of Mars and Venus. Shklovsky even predicted astronauts landing on Mars, maybe Venus, specifically to search for life. Though, he also noted, the early results were already suggesting finding even primitive life there might be unlikely. A dose of realism set in quickly.
So the focus for finding intelligent life had to shift outwards, beyond our solar system.
That's where the modern search for extraterrestrial intelligence, SETI, comes in. Scientific efforts focus specifically on detecting signals, evidence of technology from civilizations orbiting other stars. And that's an incredibly challenging task
Why so challenging? Beyond just the distance.
because it forces you to make hypotheses, not just about biology or chemistry, but about the long-term development of civilizations over thousands, maybe millions of years. What technologies might they use? How long do civilizations typically last? What motivates them? It's sociology, economics, philosophy, all projected onto hypothetical aliens, hugely uncertain territory.
So if it's built on such shaky, speculative foundations, why do it? Why spend the money, the telescope time?
Because, unlike pure philosophical speculation, SETI has the potential payoff that is, in principle, verifiable. The ultimate criterion is practice. If we detected a signal, if we made contact, then the hypotheses, however speculative, were pointing in the right direction. The possibility of empirical success justifies the effort, despite the long odds.
And Shklovsky saw this whole endeavor, this attempt to listen and understand across cosmic distances, something significant in itself.
Very significant. He saw the analysis of contact possibilities, the sheer intellectual effort involved, as demonstrating the incredible power of the human mind. Our ability to even conceive of this search, to develop the tools and theories for it, he argued, has already made human intellect a factor of cosmic importance. We're not just passive observers anymore. We're active participants reaching out.
That's quite a journey, from animating the moon and stars in ancient cults through philosophical debate and religious persecution.
To Mitrodorus and his wheat field, Bruno at the stake, Herschel's inhabited sun.
All the way to stellar evolution, DNA as information, Sputnik, and the equations governing potential interstellar communication.
It's gone from pure belief, often based on assuming similarity, to a concrete scientific problem defined by physics, chemistry, biology, and the vastness of cosmic time.
So we've established the planets are likely numerous, we understand the basic chemical requirements, we grasp the need for stellar stability. We're poised, scientifically, better than ever before. What does this all mean for us right now?
Well, it means we're finally asking the right questions, I think. We've moved beyond just assuming aliens would be like us, living on Earth clones. We recognize the need to understand evolution, stellar evolution, chemical evolution, biological evolution. But the core challenge, the thing Tsiolkovsky hinted at a century ago, remains immense.
The difference in development levels.
The potentially staggering difference. If civilizations are common, they likely started at wildly different times, millions, maybe billions of years apart. So the final thought, the really provocative question this whole history leaves you with is this. Given those potential gulfs in time and development, if we ever do make contact, if we detect something,
Will we even recognize it?
exactly, will we be able to comprehend a civilization millions of years more advanced, or even one that evolved down a completely different biological or technological path? Could they be so different, so advanced, or perhaps so alien in their very nature that they operate on principles we simply can't grasp with our current understanding? Answering that requires thinking on a truly cosmic scale, far beyond our everyday human experience.